So now we're going to be showing how properties of the graph of f of x are going to be determined by the derivatives f prime and f double prime. So starting with the first derivative rule, we're going to have a couple rules in this section, and the first one is the first derivative rule. So if f prime of a is positive, if the derivative at a point is positive, that means the function is increasing at that x equals a point. And similarly, if the derivative is negative, f prime of a is negative, that means the function is decreasing at that x value. So positive derivative, the function is increasing. Negative derivative, the function is decreasing. And notice that this rule doesn't say anything about when f prime equals 0. So when the derivative equals 0, this is actually going to help us with the relative extreme points, but this rule doesn't tell us anything about when the derivative is equal to 0. So let's see these examples here with these graphs. This first example on the left, we can see that the function is increasing, and that means the derivative has a positive slope. The tangent line has a positive slope. For the one on the left, we can see the function is decreasing because it's falling left to right, and the tangent line has a negative slope. Okay, let's do a couple examples here. Let's sketch the graph of a function that has these 4 properties. So the first property is f of 3 has to equal 4. So I'm just going to go ahead and put f of 3, 3, 4, put a dot at 3, 4 to start off. We know that f prime is positive for x is less than 3. And a positive derivative means the function is increasing. So everything less than 3, the function is going to be increasing. And we know that f prime of 3 is equal to 0. That's going to mean a relative extreme point. Or for now, let's just say the tangent line is going to be 0. Or the tangent line is horizontal, rather. Horizontal because the slope of a horizontal line is 0. And then for D here, we have f prime is negative when x is greater than 3. Negative slope means f is decreasing. So everything after 3, it's going to be decreasing. So what we can do, we can just fill this in something like this. And that would actually be good enough for a function. Nothing too complicated. It's, I guess, not technically the only graph that you could draw for it, but that's the simplest one you could draw. We have it's increasing for less than 3. The tangent line at 3 would be this tangent line, which means it would be 0. F prime of 3 would be 0. And then the slope is negative for everything after 3. Okay, so that's the first derivative rule. The second derivative rule is going to tell us about the concavity of the graph of f of x. If f double prime is positive, that means that f prime is increasing, which means the slope is increasing. And that's what means concave up. And if f double prime is negative, that means f prime is decreasing, which means the slope is decreasing, which means concave down. So in the last section, we weren't really using that terminology too much because it gets confusing. So we won't really be talking about slope increasing or decreasing too much. But the second derivative rule, what this actually says is that if f double prime of a is positive, then f of x is concave up at that point. And if f double prime of a is negative, then f is concave down at that point. So that whole thing up there is the second derivative rule. And also notice here that the rule doesn't say anything about when f double prime of a is 0. It could be concave up, concave down, or there could be an inflection point, which we'll see in a little bit. So here's a little table that shows how the combinations for these properties with increasing, decreasing, concave up, and concave down. So there's 4 different cases. 1, 2, 3, 4. If, for the first one, let's look at the first one. If the derivative is positive at the point and the second derivative is positive, that means f is increasing and f is concave up, and that would be this graph over here. And if for 2, if f of a is positive but f double prime is negative, that means f would be increasing, but f of x would be concave down, so that would look like this graph over here. And then for the third one, if f prime is negative and f double prime is positive, f prime being negative means the function's decreasing, and f double prime being positive means it's concave up. That would look like this graph over here. And for the fourth rule, if they are both negative, both derivatives are negative, that means f is decreasing, f is concave down, and that would look like this graph over here. So these are the four kind of main graph shapes for a certain point. And let's go ahead and sketch the graph of a function with all of these properties. So the first one, nice and easy, all of these points have to be on the graph. So 2, 3, 4, 5, and 6, 7. So all of these points are on the graph, so that one's good. And for the next one, for b, we have f prime of 6 is 0, and f prime of 2 is also 0. And that's going to be a horizontal tangent line. It could possibly be a relative max or a relative min. It technically doesn't have to be either just yet. So we'll see about that in a second. For c, we have f double prime of x is positive for x less than 4. So everything less than 4, the second derivative is positive. That means concave up. So that's how I'm going to abbreviate concave up, CCU. And for everything greater than 4, the second derivative is negative. That means it's going to be concave down, CCD for concave down. And then f double prime of 4 is going to be 0. And this is going to be an inflection point because it changes concavity at x equals 4 based on the previous two properties. So let's go ahead and apply all of these. So everything less than 4 is going to be concave up. So if we do something like this, that is concave up, and we have a horizontal tangent line at 2, at x equals 2, which is what we wanted. So that one's good. And now if we go everything greater than 4, it has to be concave down. So that might be something like this. So that's concave down over that interval, and once again we have a horizontal tangent line right here at x equals 6 because that's what we were told to have. And it looks like everything is satisfied. We have this inflection point at x equals 4 where it changes concavity. Concave up to concave down. Okay, so now for the connection between f of x and the derivative f prime of x. And we should be thinking of the derivative of f prime, as the slope function for f of x. So what that means is that the y values for f prime of x are the slopes of the corresponding points for f of x. So taking a look at this example, we have a function f of x is negative x squared plus 8x, and that's graphed over here on the left. And we have a couple slopes, or a couple points graphed on the function with a couple of their slopes. And then on the right, we have the graph of the derivative. So we want to know how is the slope changing in our function f of x, and we want to compare the slopes on the graph with the y coordinates of the points on the derivative. So first notice that the slopes are decreasing left to right on f of x. We have 6, 4, 0, -4, -6. So they're getting smaller and smaller as we move left to right. And if we want to compare those values with the y-coordinates of the derivative function on the right, we have a slope of 6, and that is the y-coordinate for the derivative. Then we have a slope of 4. That is also the y-coordinate for the derivative. Notice it's in the same x position. Slope of 0, that's the y-coordinate for the derivative, and so on. Slope of -4, y-coordinate, slope of 6, y-coordinate, which will happen every single time because that is the relationship between f of x and f prime of x. And let's do one more question here. We have the graph of the derivative. So that's important. We're given the graph of the derivative. We're not given the graph of the function. We're given the graph of the derivative function. So first we want to know what is the slope of f of x when x equals 1. So f prime of 1 equals 2. It has a y-coordinate of 2. That means the slope of the function at x equals 1 is 2. For the same reason on the graph on the previous example. And for b, describe how the values of f prime change on the interval 1 to 2. So from 1 to 2, that's going to be from here to here. And the values are decreasing, and they're still positive. So they're still positive because they're above the x-axis. So that means the function is still increasing, but it's increasing at a decreasing rate. So for C, putting that together, the shape of the graph of f of x on the interval 1 to 2. So since the slope is positive and decreasing, this means that f of x is increasing and concave down. So that would look something like this. F of x would look something like this over the interval, where it's still increasing, but it's increasing at a decreasing rate, meaning it's concave down. And for question D, for what values of x does the graph f of x have a horizontal tangent line? Horizontal tangent line means f prime of x equals 0. So let's see where it equals 0. F prime equals 0 right here at 3. So that's going to be at x equals 3. So f of x has a horizontal tangent at x equals 3 because that's when f prime of x equals 0. And then for E, we want to explain why f of x has a relative minimum at 3. So a relative minimum at 3, and that is going to be because the slope changes from positive slope to negative slope, and then a slope of 0 between them. So if it goes from positive to negative for the slope, that means the function goes from increasing to decreasing, which means relative maximum. So that would look something like this, where f of x is increasing. F of x is increasing and then decreasing. So it would have to have a relative maximum at that point. And then over here, if you want to take a look at the graph of f of x compared to the graph of f prime of x, they're graphed on the same exact xy plane. Take a look at them and kind of verify everything that we just said. Okay, so that is it for this section.